All right, let's get started for today. Welcome to lecture. A couple of announcements. Project 2, hopefully you're already working on Project 2. It's due on Friday at 5 p.m. There's an optional contest that you can work on till Sunday night. Then homework 4 is out, and it's due as usual for homework on Monday evening. So this week was the exception, right, because of President's Day, but homework 4 back in the normal schedule, due on Monday evening. All right, reinforcement learning. So in reinforcement learning, we'll be looking at problems where kind of some of the classical stories are things where you would say, oh, how do you train a dog, right? How do you teach it something? Well, if it does something good, you say good dog. If it does something bad, you say bad dog. And it starts somehow getting the gist of that. Maybe give it food if it does something good, no food if it does something bad. And after a while, it learns what the things are it should do to get high reward and what the things are it should do to, I guess, avoid the really bad rewards. So what does it look like formally? You have an agent, and the agent can take an action at a given time step. Then things will change. Due to the environment, the agent itself, if the agent is a robot, it could be part of the agent itself that changes. The state encompasses everything that matters to the problem. So state might change. Then a reward might be distributed to the agent for the state, action, state triple that just incurred. And then the process repeats. So that's the reinforcement learning setting. It keeps repeating, you're in a state, take an action, might get a reward, land in a new state, keep going. The goal of the agent is to maximize the expected rewards. And the interesting thing here, different from what we've done before, is that everything that's supposed to be done here is based on these samples. So before we used to say, oh, here's an MDP and here's a transition model, here's the reward function, compute what's optimal to do. Not in reinforcement learning. In reinforcement learning, this is all you get, this cycle over here. And based on that experience, you somehow learn to do well. All right, so let's look at an example. This is going back to the robot soccer example from the first lecture. So we'll look at here the problem of learning to walk. So these are the robots you get to deal with, and you can imagine as you want to play robot soccer, you want them to walk fast. And we'll look at what happens before learning. And with before learning, what I mean is somebody went in and somehow hard-coded a policy, said, well, I think to walk well, you need to do this sequence of motor motions followed by this sequence of motor motions and so forth, and hoping that that is somehow meaningful. That's really hard to do because it's really hard to kind of think about what would happen if you are a robot dog and exactly what the results would be of each motion. Then we'll see what happens during learning, and that will be reinforcement learning in action. We won't know yet what's happening underneath, but it will see the result of reinforcement learning, and then we'll see after 1,000 learning trials how well the robot dog can walk. So here's initial, which means hard-coded. So robot's walking. It's making progress, but you can also see often the front feet are slipping back. It's not going super fast, but at least it is a walking motion. It's not moving at all. All right. Then what they did to play these robot soccer games, they would put their robots on the terrain where they're going to play the next game. Right before the match, there would be some training time, so you could fine-tune the control policy that robot is using through reinforcement learning to maybe do things like adjust to the specifics of the terrain. You can imagine that how much friction you have on the terrain will play a big role in exactly what the right gait is that you should execute. And so that's what they did when playing these games. And this is an example of the training phase. So here it's somewhere in the middle of the training phase. It's already making faster progress than it used to in the initial hard-coded policy. And then here is what you get once it's finished training, fully converged. And so it walks a lot faster than the hard-coded policy was able to achieve. All right, let's look at another example. This is an example from Russ Tedrick's group, or I guess actually he was still a PhD student at the time. So Russ Tedrick as a PhD student in Sebastian Sung's lab at MIT. What they looked at is also the problem of walking, and what they did is they built this robot here. If you carefully look at this robot, and you'll see it in the video too, it's kind of built such that its feet are curved, and so if you push it a little to the side, it'll just kind of waggle left, right. And if you give it a little bit of forward momentum in some sense, let's say put it on a downhill slope where it'll then naturally kind of swing a leg down, it'll start walking. So it's passively already capable of walking on a slight downhill slope. So some work went into the design, but then now you put it on a flat, you somehow need to put energy into the system to make it walk. And the reinforcement learning here is about how to exactly make that happen. The actuation is in the ankles here. So the ankles have actuation, 2 motors per ankle, 4 motors total. And here's what happens if you run reinforcement learning on this Toddler robot. So the waggling motion is natural, keep that in mind, but it's trying to kind of insert more energy into that and also see if it can get a forward motion out of it. So here it's already walking, maybe not in a very directed way, but it's not waggling in place. It's getting better and better. This can take a while, as you'll see in your experiments. It can take a lot of trials before you really learn to walk, but before you know it, your robot's off to college and leaves you behind. Teresa Zhang actually is right now a PhD student in the mechanical engineering department in Berkeley. She was an undergrad at MIT when she worked on this. All right, let's take a look at what you will do in your project 3. One of the things you'll do. This is the crawler robot. The robot consists of a box right here, and then this leg sticking out or pin sticking out. You have control over this joint angle over here and this joint angle over here. So 2 control inputs, 2-dimensional action space. And the goal is to make it progress. So let's take a look at what can be done. So it happens to be running Q-learning at this point, which is an algorithm we'll understand by the end of this lecture. But so what you see here is effectively feeling out how the system works. It doesn't have a model for what will happen if it takes an action. It has to try actions to understand what the consequences are of these actions. It doesn't even know where the reward is. Before it's acted at all, it doesn't know that moving to the right happens to get a high reward. But once it's done that, you can imagine it could start understanding when high rewards come in, when they don't, how that relates to actions it takes, and so forth. And then if you run what the algorithm will be looking at, skip a million trials ahead. It's doing a little better. One thing I'm going to do is I'm going to lower this number. That's the amount of randomness infused. The randomness helps in terms of exploring what it should be doing. So you see after a million steps, it actually has learned to crawl off to the right pretty well. So that's something you'll be able to build yourself in your projects 3. All right, so actually, why 3 examples of walking? Well, it turns out that reinforcement learning doesn't just apply to walking, but it's a nice example because in walking, if you look back at the robot we were just looking at, let's be very explicit here about what's going on. Once it's learned, so we take a million steps ahead, reduce the randomness here. Even though it's learned to make progress, you see that at times it's not making progress at all. And this is pretty typical for walking for many robots, is that you're not making steady progress at all times. You're alternating, maybe getting ready to lift your leg, move it forward, and then pull your body forward. And so the reward is it's not instantaneous reward you care about. You need to think ahead and think about how much reward will I get on the average over time if I take a certain sequence of actions or follow a certain policy. And walking is a good example for that, in that it tends to be this characteristic that you need to think ahead and think of the future sum of rewards. All right, so even though I've said we're not going to be given an MDP, we still assume that there exists an MDP. Underneath the whole system, there is an MDP. There is still a set of states. There's still a set of states, a set of actions, a transition model, which is stochastic, a reward function, and we're still looking for a policy pi that maps from any given state to hopefully the optimal action. But the new twist is that now we don't know T or R. We might find out a little bit about T and R by acting in the world and seeing what happens for certain states when taking certain actions and so forth. But initially, we don't know T and R, and that's the big difference. All right, so offline versus online is the big difference between today's lecture and next lecture and the previous two lectures. So today and next lecture, we're in this category. The previous two lectures, we were over here on the left. Offline planning means you're given the MDP, you plan offline, find the optimal policy, and for this particular problem, you'd probably find a plan that says, hey, I should always go straight to avoid the fire pits. Online planning, you have to do learning. In RL, the first time you enter this scene here, you know nothing. You just know what actions are available to you. You know which state you are in, and that's it. You don't know how that state relates to other states, and you just choose one of your actions and you see what happens. And until you've actually taken an action, you have no idea what happens. In fact, even though in this example, you might think, oh, I can see the fire pit. That's not how RL is set up. You cannot see a fire pit. There's no such knowledge of there are fire pits that could be bad. You just say, oh, I could move east. Let's see what happens. And then the reward is really negative. And they say, well, maybe I try west. The reward is really negative. Then you move north and you say, oh, this was not negative at all. And you kind of keep acting and see what happens, learn about the world, and hopefully learn to act better over time. All right, there's many ways to learn. First thing we'll look at is model-based learning. And the idea here is that you assume there is some model, but you don't know the parameters of the model. And from the experience, you're going to then estimate the parameters of that model, and then use that estimated model to, let's say, plan with that estimated model, and hopefully that estimated model is accurate enough that you get a good plan out. All right, so we learned an approximate model based on experiences.
For the walking 2 slides ago, like before it used to be 80% chance of doing what you wanted, and then 10 would go to either side.
Yes.
So on RLs, then you might tell it to go straight and it cuts off on the side. Will the machine know that it didn't do what it wanted to do, or will it think that it went?
So that's a good question. What are our assumptions in this grid world when we take, let's say, action north and we go off to the west, which was not intended? The system doesn't know that it was not intended, because the system, in fact, won't even know what north means. There's just 4 things to choose from that have no meaning initially. North is something we give it a name, but as a reinforcement learning agent, you don't have that name, or even if you have the name, you don't know what it means. So when you try to go north, so to say, and you go off west, you might have learned if you do that action only once that the action north in that state means going off west. And that's all it knows at that point. Okay, so this is the main idea. You collect experience. From that experience, learn a model, then use that learned model, and then you run, let's say, value iteration or policy iteration to find the optimal policy for the learned model, which in this case, learned model means learned reward function and learned transition model. All right, so step 1 is learn the empirical model. So that's estimating T and R from experiences. Step 2, value iteration, policy iteration, whatever you prefer. All right, let's take a look at this in action. Let's assume gamma equals 1, and we have some input policy pi, because we need to take some actions, right? And we start, and this is what we observe. Call this training time. Often training is what happens in the beginning, and then testing is what happens later when you want to evaluate how well you're doing. In general reinforcement learning, they might end up being interleaved, that you don't want to train and test in separate stages, but in model-based learning, that's one way to think of it, is you are first training, you collect data. Your first episode, this is what happened. You started in B, took the action east. You have no idea what that means, but you ended up landing in C, got a reward of -1. From C, you took action east, landed in D, got a reward of -1. From D, the only action available, exit, I guess, that's the one you take. Land in D, done state X, got a reward of +10. So that's what this means. That's one episode. That episode's over, you're in the done state, you get reset somewhere in the MDP, some state, act again, get a second episode, a third episode, a fourth episode. All right, so what can we learn from this? Well, here's what we can learn. We can learn an approximate transition model and an approximate reward function. How do we find this number over here? The estimate for the probability when being in B, taking action east to land in C. Well, we look at everywhere where we're in B and take action east, which happens twice. Both cases, you land in C, so then the estimated probability is 1 for landing in C. How do you get this one? Similarly, we look at any time we were in C and took action east, which is here, 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 and here, 4 times. 3 times we landed in D, 1 time in A, so the probability for D is estimated as 0.75 and for A 0.25. Similarly, we can look at reward we got in those situations. For C east and landing in D, we got -1 every time, so that's our estimate. In fact, the rewards in our setting are deterministic, so once we've seen a state action state triple once, we know what it's going to be, and we can just read them off. So now we have a learned model. Is 4 episodes enough? Probably not to learn a good model. You might want more training episodes than 4, but if you had 4, this would be your estimate. At this point, value iteration or policy iteration using this learned model, that will return to you a not necessarily optimal, but hopefully a reasonable policy, and you're done with model-based reinforcement learning. That's our first algorithm. All right, so we've seen one algorithm. This is actually quite a popular algorithm. It's great if you have the capacity to store all the data, all your experiences, so you can estimate the models, because in some sense, this is all the information you have, right? You're using all the information you got in a very efficient way here. Efficient in that you're not losing any information. Maybe less efficient in that you do need to go through this intermediate stage, which we'll later see you can avoid. You can actually avoid building a model and then doing planning with the model. You can learn directly. But if you have the time to first learn a model, this is a reasonable way to go. Okay, so let's take a look at model-based learning versus model-free learning. Let's say we want to compute the expected age of CS188 students. Okay. Well, if we had a known distribution over age, then here's what we could do. We can compute the expected value. We sum over all possible ages, the probability of that age multiplied with the age, and that gives us a weighted average of the ages, the way that we need to do to get out the expected age of CS188 students. What if we don't have the distribution? We need to somehow learn. We need to get maybe samples from that distribution to get an idea. Well, so we collect samples. Let's say we get capital N samples of ages. How can we use these samples? Well, the model-based approach, which actually might not be the most intuitive one, but this is the model-based approach, and it's a reasonable approach, is say, well, we don't know P of A, the distribution for age. First thing we do is to estimate that distribution for age. So for each age, the probability, as we estimate it for a particular age A, is the number of times we see A divided by N, the total number of samples. Once we have that approximate distribution, we can then estimate the expected age using that approximate distribution, using the same equation as we had over here, but P of A is replaced by P hat of A, which is our estimated distribution. There's another way to do this. If you have these samples here, you want to estimate the expected age of CS188 students, you can bypass this process. You can just say, oh, all I need to do is to average the samples, and I know that's going to be a reasonable estimate if I have enough samples of the expected age. So the left thing works, but the right thing works too, and in some sense is simpler. And for the remainder of this lecture, we're going to look at a generalization of this way of learning, not for estimating your ages, but for reinforcement learning. rather than first going through the process of estimating a transition model and a reward function explicitly. One thing to think about when you look at these two equations here, look at this equation here, and this will come back in reinforcement learning, this equation here, there's a difference there, right? On the right, what you see is that we just have an age here, and we weight all of them equally and divide by n. On the left, for each appearance of age here, we weighted by p hat of a, so they're not equally weighted. Why is that happening? Well, on the left, the reason we weight by p hat of a, that's the way the expectation is set up, right? You need to weight each possible outcome of the random variable by its probability. On the right here, the reason we don't need to weight it is because naturally when we get samples, ages that are more likely, that have a higher probability, will just show up more often in this sample set. And so through the sampling process, we automatically get more frequent occurrences of the more likely ones, and hence we don't need to explicitly weight them anymore. They just appear more often, and so we'll often have the same age appearing here if it's a likely age. Let's say 19 or 20 would probably appear a lot in this over here for this example. All right. Model-free learning in the context of reinforcement learning. First we'll look at, so we'll make another distinction here, passive learning versus active learning. In passive learning, it's like watching a video of something going on and learning from watching that video. You're not in control of what's happening. You might see the other robot jump in the fire pit, see how much reward they get and so forth, and you might then learn a value function for that other robot in the world it's acting in. In active learning, you get control. In active learning, you'll get to choose the actions you take, and as you can imagine, it gives you the ability to explore explicitly and learn more effectively. But we'll start with passive learning. Yes? Yes. So if we go back and we look at what we did here, in this example, which is the one you're referring to, right? Here we didn't talk about how these episodes were generated. If it were active learning, you'd be generating the episodes yourself. You'd have to think about what actions to take to generate interesting episodes. If it were passive learning, you would just be observing episodes. We didn't make the distinction here. We'll come back to it later. But for now, just assume they were given for this model-based learning example here. So passive learning, we assume a policy pi is given, is fixed, so we don't get to choose actions. Somebody prescribes the actions for us. We still don't know t and don't know r. We'll have to learn the state values. That's what we're interested in. So we're interested in this case, v pi for each state s is what we're interested in. We want to know what's the value under the policy we're observing of each state s. All right, so the learner is just along for the ride. No input to what happens, but hopefully can learn those values. This is not planning, right? We're just watching things happen and trying to learn what the values are. Okay, here again, we have another branching here. We have different things we can do. The first thing we can do is direct evaluation. What that means is you compute values for each state under the policy pi by just averaging together observed sample values. It's a lot like estimating the expected age of 188 students by taking a bunch of samples, averaging them. That's exactly what's going on in direct evaluation. All right, so that means that every time you visit a state, you should write down what the sum of discounted rewards was that you got after visiting that state, and that's one sample for that state. Next time you visit that state, you again write down the sum of discounted rewards you got since visiting that state. That's the next sample. After acting for long enough, you have a bunch of samples for each state, you average them, and that's the way you estimate the value of the policy for each state. So let's look at an example here. So we're back to this over here. These were our episodes, right? What values do we get out using direct evaluation? So let's say we're interested in V pi of state C. Well, after visiting state C, we've had here, let's say discount factor is 1, makes it easy to do the computation. We've had 9 here as overall after C. Here we got 9. Here we got minus 11. And here we got 9. All right, so what's the average? That's what we work with here. Right? Our estimate says, we estimated by 9 plus 9 plus 9 plus minus 11 over 4, which will be some number. We can do the same thing for each one of these states. Check after we visit the state, how much reward do we incur, and then take the average. So let's take a look at how that all plays out. So we have these values here. Okay. Take a look at this. Anybody see any issues with the values that were just learned? Any weakness to this approach? Over there. So the observation here is spot on. What's unsatisfactory about these estimated values here is that even from just those 4 episodes, that little bit of experience, if we look at what happened in those 4 episodes, when we started in E, which happened just once over here, we started from E, we happened to get, is this even? No, happened twice. Twice we started from E, we got once an 8, the other time minus 12, the average is minus 2, right? Which is indeed what we're seeing here. But we know what happened when we started from E every time we landed in C. That's always what happened next. And a lot of the rewards came after having passed through C. They didn't come right away going from E to C, they came after C, right? Just happens to be the case that we visited C 4 times. Each of these episodes went through C. And on the average, after visiting C, we get plus 4, which is shown here. But the value of E doesn't reflect that. It doesn't reflect the fact that on the average after visiting C, we get plus 4. It just reflects that when we came from E and then visited C, on the average we got minus 2, just based on 2 of the episodes rather than using all 4. So we're not using the information that from E we tend to go to C, and we have a much better estimate of the value of C, because we can look at all episodes. Then if we just look at these 2 bottom episodes here that happen to also start in E. So what we really lose here is the connection between states that we visit one after the other, right? The equation we've looked at many times in previous lecture, the Bellman equation, which tells us that the value of a state is related to the reward you get instantaneously, plus then the value of the next state, and then you average this over possible next states. That information, we have that information. We know that's true, and it's not going used here. We're ignoring that information. All right, so what's good about it is that it's easy, simple. You know that if you get infinite amount of runs, it'll converge to the right thing, right? Averages will get the actual expected value if you have enough samples. But the bad thing is we don't learn about the state connection. So we waste that information, and we know we could have better value estimates from what we've seen than the ones we're getting when we only have a finite number of samples. Okay, so the B and E, this is the issue we discussed. So why not use policy evaluation? We saw policy evaluation in last lecture. We said, well, what do you do in policy evaluation? Well, this is what you do. You start with the value for 0 time steps left is 0 for all states. Definitely could still do that. And then to find the value for k plus 1 time steps left, you recurse and use the value for k time steps left. What's the problem with using this equation over here? Well, we're in the reinforcement learning setting now, so we don't know t. We don't know R. That's a problem because you need them in those equations. At the same time, if you look at that equation, what's going on here? It's some kind of averaging, right, of quantities over here. So you can start thinking about, can we do something where even when we don't have a model, maybe we can still use this equation based on samples somehow. We see samples, we see things happen, and based on these samples, we're going to approximate, we're not going to directly estimate T, that's model-based learning, but we're somehow going to see samples, and we know that by averaging those samples, we get the equivalent of using the weighting by this transition model. And that's what we're going to be after now. So we need T and R to do this as shown here, but let's see if we can avoid this. So we want to compute these averages, but from samples rather than using T and R explicitly. Okay, so let's say you take samples of outcomes S prime by doing an action and average, right? So you're in state S, you took your action pi of S, you landed in state S prime. Let's say S1 prime the first time. Now let's say somebody can put you back into state S. You again take your action pi of S. You transition into state S2 prime. You get a new sample. You keep repeating this until you have sufficiently many samples. And now you can say, well, I've seen all these samples. These are samples of the quantity on the right-hand side here, of this thing over here. Note that we might not know what these values are yet, but let's not worry about that. Let's assume we somehow have access to the values of the next states, just for now. Then we would get a bunch of samples of the right-hand side. We don't need this weighting anymore because the number of times we see each sample will relate to how likely that outcome is. And so we can just average these samples and get a sample-based estimate of the value of the state S. So there we go. That's our sample-based estimate of the value of the state S. And then we can, in principle, we can do this for one time step left, and we repeat this. Once we've estimated all the values for one time step left, based on a bunch of samples, we keep acting, we get new samples, we do it for 2 time steps left, keep repeating. In there, we do it for all states and so forth. So you can see how, in principle, this might work out. What's the issue still, though? There are 2 issues left for us here. One of them is that we assume that this was available here. And while in principle, maybe you could do that if you got a lot of experience, you could start with saying V0 is available, so we can start with from V0, go to V1, and work our way up, but it would take a really long time. The other thing is that we assume we can visit state S again and again and again. We're acting in an MDP where we don't know the transition model. We don't know how to get to different states. So we don't have the ability to just go visit the state S again. It might happen, might not happen. That's an exploration problem. We'll get back to that at the very end. For now, we'll worry about this over here, the fact that we kind of don't have these things available. Yes?
So we can't just start at, like, say, the starting line? Like in the dog example,
Sometimes you can, sometimes you cannot. It depends on the type of MDP. Even if you can, you still need to have a strategy. You need to have a strategy that decides for you when is it time to reset and where to reset to. And that's something we need to think about, what the right thing is there. All right, so we're almost there in many ways to get rid of the model and just do a sample-based estimate of the value of a policy for each state. We have a couple of issues left. Unless, of course, you're a magician who can look into the future and teleport from state to state as you like. We need something new that we haven't covered yet. So we learn from every experience. That's going to be the main idea. We update V of S, and note that it's now this really V for the particular policy pi. So annotate with pi. But we're not annotating with K anymore. So to avoid this kind of doing this building up from 0 to 1 and so forth, we're going to just learn directly the value of the policy, assuming infinite horizon, discounted sum of rewards. Okay, how does this play out? Well, let's let's take a closer look at what the equations look like. All right, effectively what we'll be doing is computing a running average. So every time experience comes in, we will average in the new sample with what we already had. So we have new experience, S, pi S, S prime. From that we have a sample estimate shown over here. We use our current estimate of V pi of S prime, which might not be accurate in the beginning, but we'll just use it. We already have a running average for V pi of S, and we average between the two. Alpha is a number between 0 and 1, so you have a weight, 1 minus alpha on the estimate you already had, a weight of alpha on the new sample. There's a different way of writing this by reorganizing terms, and sometimes that's the preferred way. You can write this way. It has a different interpretation. That's why it's interesting to sometimes write it this way. You keep what you had as your estimate for the value for the policy pi state S, but then you nudge it a little bit. Alpha is the scaling of how much you're willing to nudge it, and in which direction you nudge it is determined by the difference between the sample value and your current estimate. If the sample value is higher than your current estimate, you'll nudge the value up. If the sample value is lower than the current estimate, you'll nudge the value down. So you move it in the right direction, and how much also depends on how large this difference is here. Yes?
So this update you talked about, is volume still being 100% or volume still being like 1%? Or is it you do an update after?
What we do here is, as we're acting, as we go along, we run this update, and we can throw out all experience we've had so far. We just keep around the value function, V pi, a value for each state S. That's all we keep around. We look at the current state action state transition, the reward associated with it, and then from that compute this estimate over here, make an update to the value function that we have stored, and then we take our next action, keep repeating. So we don't have to store all experience like we had in the past to build models and so forth. All right. Now, what's happening here is not an actual average, right? Because we're weighting by 1 minus alpha and alpha. It's an exponential moving average. So what happens here is, if you do this kind of averaging, right, this is the type of update we're looking at. The new average after n samples is 1 minus alpha, the current average after n minus 1 samples, plus alpha times the new sample xn. If you write out what actually happens, you get something like this in terms of the original samples. What's interesting about this is that the latest sample is weighted the highest, and the previous one is weighted second highest, and so forth, and the very earliest sample is weighted much less so than the later samples. And then you need to divide by something here to make sure they actually have a weighted average, not something that is the weights in this average have to sum to 1. This is actually a good thing. At first you might say, well, there's not a real average. That's too bad. We wanted a real average. This is not just good because it's convenient. It's a simple update rule, and you don't need to keep track of data the way you might otherwise want to. It's actually the thing we want. Think back of the equation we had. The equation over here. Right? This is our update equation. Well, as we do these updates, the samples we use, sitting right here, right, is the value of the policy pi at state S prime. Initially, that's a very bad estimate. In fact, initially, it's probably very far off. So your initial samples are rather inaccurate. But then thanks to this process, even though it's inaccurate, you get a slightly better estimate as time goes by. And so as time goes by, you do more and more updates. Your value estimates get better and better. And then it's a good thing that the old samples get weighted less and less as time goes by, and the new ones get weighted more highly. It's a little bit of fine print there, actually, to make this guaranteed to work. It's actually something you need to do where alpha will need to decrease over time. So alpha will need to get smaller and smaller as you progress in your learning. Because if alpha stays fixed, if there's randomness in your transitions from state S, sometimes you go to state S1, sometimes to state S2, then the sample value will one time be related to the value of state S1, the other time to the value of state S2. If alpha doesn't go to 0, you'll keep hopping around between different values. right? But with alpha decaying to 0, over time you'll converge. You don't want to go to 0 too quickly. If you go to 0 too quickly, then you don't get the right estimate. Question there. There are many choices for alpha. So to make this concrete, we want alpha to decrease. So one option is to say alpha at update n is 1 over n. That's one option. You can do more complicated things. You can say, well, I might want it to depend on the state that I'm in. So maybe the alpha I'll be using depends on the count for that particular state S, how often I've been in state S, and then it might be 1 over the count for how often I've been in state S. You can do even more complicated schemes. Technically, key to make this work is that sum over k, alpha k, k from 1 or whatever, 0 or 1 to infinity is equal to infinity, and that the sum of k equal 1 to infinity of alpha k squared is smaller than infinity. This is beyond the scope of the course, but technically what's going on here is that this thing over here is ensuring that the variance of your estimate is bounded. You don't get infinite variance in the process. This thing over here is ensuring that if you are unlucky in the beginning with the samples you see, you can still fully correct it. You don't want your corrections to be bounded. No matter where you are in time, because this sums to infinity, that means from then onwards it will still sum to infinity, otherwise it wouldn't sum to infinity, which means that no matter how unlucky you might have been, you still have the leverage to correct for it, because you still have this infinite power, so to say, to overrule anything unlucky that might have happened. Okay, so let's look at this in action. This is called temporal difference learning, and the reason it's called temporal difference learning is because if you phrase it in the way that we saw in the second line there, where you don't take the average between sample and current value, but you say it's the current value plus a nudge towards the difference between the sample value and the current value, that's where the term comes from, temporal difference learning. All right, so let's say you start running with some policy pi, you're in the state B, you take an action, you observe a transition, from B you end up going, taking action east, landing in C, getting somehow a reward of -2. Then what you do? At this point, you look at the equation, you do your update, right? We're showing the current values, 0, 0, 0, and 8. So what will happen is, with this one transition, only one value will change. Just the state you just left will its value C changed. So for state B, right here, value will potentially change. For the other states, things just stay the same. What do we get for B? Well, 1 minus alpha, alpha is a half, so this is going to be a half, times the current value of that state, which is 0, plus alpha, which is a half, times the reward, which is -2, plus gamma, which is 1, times the value of the next state, which is 0, so we have plus 0 here. And we see that we end up with -1 as our new estimate for the value of state B. Okay? Next transition, from C, we take the action east, land in D, get a reward of -2. What do we have now? We start in state C, which means that the only state that will change value using temporal difference learning will be state C. The other ones stay the same. So we still have -1, 0, 0, 8. And for state C, we can compute what's happening. 1 minus alpha, in this case, is 0.5. The current value of state C, which is 0, plus then alpha, which is 0.5 times the reward accumulated right now, so that's -2, plus gamma, which is 1, times the value of the next state, the one you just landed in, S prime, which is D, which is 8. So we have 8 over here. And so we end up with, in this case, -2 plus 8 is 6, times 0.5 is 3. So we end up with 3 as our new estimate of the value for state C. Question? It was just initialized this way. In practice, you might have things initialized with 0, but then it would take us a real long time to step through this example, because then we'd have to kind of move until we actually get a reward somewhere, and then things would only start propagating. So here we just initialize it in a way that makes the example more interesting. That's all. The best thing you can do in practice is to put down your estimates. If you have any way of estimating what the values might be, any prior knowledge about the problem, just throw them in there. Because as close as possible that you can start, the faster you'll get to the true values. Okay, what are the remaining problems we have here? The nice thing is that we have a model-free approach to estimating or learning, whatever you want to call it, the values of each state under the current policy. It mimicked the Bellman updates. It does a sample-based evaluation of the Bellman updates, which means we do get that connection between states that are connected to each other through the transition model. We won't get these inconsistent values that we had in the direct evaluation, so that's nice. But once we estimated the values, if we now want to act, we have nothing to use to act, right? You have the set of values. You say, oh, you're in state C. You look at the values and you say, well, what's the right action to take? No idea, because that's not, you don't act just based on the values. To act, you need to have the Q values instead. Or you need to be able to explicitly compute this one-step look ahead. If we were able to do a one-step look ahead, and we have some values, then what we could do in principle, we could run some form of policy iteration, right? You had the model, you had your values of the current policy, then you could use this one-step look ahead to find a new policy. You could use that new policy, learn the values of that new policy, and again, do the one-step look ahead to update your policy. You could interleave it all, right? You could be doing it at all times. You're updating the value and taking this one-step look ahead action, for example. That'd be some kind of policy iteration type approach. But that would still assume you have T available. It's a reasonable algorithm, but it's not something we can apply in this setting here because we don't have the transition model T. All right, so in some sense, we're still sunk if we don't know what to do. What we really would like to do is to change our algorithm. If we can change our algorithm and instead learn the Q values rather than the V values, then we can look up what the actions that maximize the Q value in a particular state, take that action, and that would be the right thing to do, presumably. So let's take a short break here, and then we'll look at how we can directly learn Q values. All right, let's restart. Any questions about the first half of lecture? Okay, so as a recap, where are we at? We were looking at problems where we don't know the transition model, don't know the reward function, but we know that they exist. It's still an MDP. And we want to learn to act through acting in that world, build up experience, and do better and better over time. We then had a two-way split in terms of approaches. Model-based versus model-free. Model-based means you use your experience to estimate T and R, and then use the estimated T and R to find optimal policy according to those estimates and act according to that policy. The other branch was model-free. We saw that you don't necessarily need to build a model to be able to estimate certain quantities, so we said, can we do the same thing in RL? Can we directly estimate values? And we saw we can, and we've seen how to do so in two ways. We've seen how to do so with direct evaluation, which means you just, for each state, keep track of the sum of discounted rewards that you've seen after visiting that state. Whenever you visit that state, that makes for one sample, the entire sequence of rewards afterwards. You stack up those samples, average them, and that gives you an estimate of the value under that current policy for that state. We know that works in the limit. If you collect enough experience, you will get the right estimate of the value of that policy for each state. What was disappointing about it is that when we had, for example, just 4 episodes of experience, is that the connection between states wasn't leveraged. We could see in that example that, well, from that state at the bottom, we were always moving up and then off to the right. But the estimate of the value of the state at the bottom was only based on whenever that state at the bottom was really visited. Whereas we knew we should use information from that next state if we have a more accurate estimate of that next state, not just the experience when we started in the bottom state. And that connection is the Bellman equation, is telling us that connection. We looked at that. We said, well, the model appears. And we said, well, we can avoid that. We can do a sample-based approximation of the Bellman update equation for a fixed policy. And that's what we ended up with over here. This is temporal difference learning. Whenever we have a state action state transition, it's a sample estimate computed this way of the value of that state, and then we average between our current value estimate and this new sample. Or another way to look at it, we keep the current estimate, but then nudge it a little bit towards the sample, the way the sample deviates from the current value estimate. Sample is higher, then you go up. Sample is lower, it goes down. Now, the reason we weren't done is because if we want to act, so far it's been all passive observing, but if we want to act, just having the values is not enough to act. I said, well, how about we learn the Q values instead? Well, the question is, how do we do that? Can we learn the Q values? Because if we could, then we could use them to make action selections. Yes?
It seems like the only difference between Q and the other is just the transition, but then the transition we built into the averaging. So, doesn't that already account the equation we came up with doesn't already account for the Q? Because basically,
You're right. I mean, intuitively, the Qs are in there. They're somehow in there, but not explicitly yet, right? For example, right now, if you run the learning algorithm we just looked at, temporal difference learning, you just learn the value of a fixed policy. You don't learn the value of any other actions. You could definitely argue that we already know how to learn Q pi S of pi of S. I'd agree with you on that. That's the same thing as V pi of S. And you're right, we are already learning Q values in that sense, but now we're hoping to learn the Q values for all actions that are available in a particular state so that we can use it to then choose between actions. So that's the difference we're going to do.
And then my more specific, I guess, on what we're just talking about is, so that on the other side, once we have those numbers filled in, can't we just go to the highest number out of my current choices?
So that's a great question. Why can't we just go to the highest number among the choices? And the reason is to be able to know what it means to go to the highest number means to know the transition model. You could think of a mix of what we've done so far. You could say, well, if I also learn a transition model in addition to learning the value function, yes, then you could do this. There's many variants on all these. You can combine them in different ways, but the way we looked at it, directly estimating the value is not enough to be able to then decide to move in the direction of high value. You need a transition model or you need a Q function where you don't just have the pi of S entries, but more than just those entries. All right, so active reinforcement learning, as a reminder, is where you now get to choose. You don't get to just watch what's going on, so to say. You're not just driven by something else. You get to choose actions. And keep in mind that when you take that action, it's not that you are voluntarily diving into that fire pit knowingly. You just don't know what's going to happen. Happen to find out later that it was a bad idea. But as you start your action, you have no idea that that happens to be a bad action. Or at least not in the beginning, before you learned a lot. Okay, so full reinforcement learning means we want to learn optimal policies, like what we got out of value iteration, what we got out of policy iteration. We still don't know T, don't know R, at least to start out with. We get to choose actions at all times, so nobody is telling us what to do. The algorithm will have to tell us what action to take. And the goal is to learn the optimal policy / values. So the learner makes choices. As we saw at the end of last lecture with the casino game where you had a red and a blue slot machine, and you got to choose between them, there's a similar trade-off here that's going to happen, right? As you are acting, is it still worth to explore a little more, or has it looked bad enough that now it's been enough and you just stop taking that action, right? How many times do you dive in the fire pit, so to say, until you conclude, I understand that this action is terrible, I'm not doing it anymore. All right, so we'll have to kind of take a little step back, and then we'll go to Q learning, which is the final thing we want to look at. So what was value iteration? Value iteration was something where we started with V0 of S for all states S equal to 0, and then Vk plus 1 for state S, and we had to do this for all states S, was computed as, it was the reward you get from state S, taking action A, landing in state S prime, plus a discount factor times the expected discounted sum of rewards acting from state S prime onwards, which is encoded in Vk of S prime. And then, of course, you don't know what state S prime you're going to get, and you don't know what action you should take ahead of time. You should maximize over the actions, and you average over next states. All right, that was value iteration, right? And this all had a very specific meaning. Vk of S prime is the expected discounted sum of rewards if acting optimally from state S prime. We also know that converges to the actual value function, the one that encodes the expected sum of discounted rewards if you were to act infinitely long. Okay? How about we change this now? We're interested in Q functions. Can we rewrite this whole thing in terms of Q functions? Because if we can, then maybe we can directly learn Q functions. Before we do that, let's look at a little bit of motivation here. And as we present it now, it might seem kind of obvious why we're switching to Q functions, but this actually took a while in the research community to decide that this was the way to go. Take a look at this equation over here. What we looked at so far, we didn't have the max over actions. We had a fixed policy. For a fixed policy, what this is an average. Right here, it's averaging. Once you have the max over actions, it's not an average anymore. It's a max over actions up front here. So this is not something we can directly approximate from samples. You can't just have a sample and say, well, I'm just going to average them together and hope that that together will be the effect of a max and a sum happening over here. That's just not what you get from averaging samples. And so the reason we're stuck is this max up front here. It's troublesome. It doesn't allow us to do the sample-based approach. If we switch to Q values, we can get rid of that max. So let's take a look at what it looks like if we were to run Q value iteration, which is a new algorithm, which we're introducing right here. Q k plus 1 SA. What does that mean? Q k plus 1 SA means if you have k plus 1 time steps left, the first action you take is action A, you are in state S, and from then onwards you act optimally. What is the expected sum of discounted rewards? We can write that out quite similarly. We have an average over possible next states. For going to that next state, we have RSA S prime plus gamma times VK of S prime. Now the issue, of course, is that if we want to do something called Q value iteration, we don't want the V values in there, so we need to get rid of this thing over here. But we have Q values now, so what we can put here is the max over all actions A prime of Q S prime A prime, and this is for K time steps left. Right. This is identical to VK S prime, right? But we're working with Q values now, so we don't want the V to appear. This is Q value iteration, running this approach here. Let's put it in typesetting. All right, what just happened here? We have an update equation. We don't know T, we don't know R when we do reinforcement learning. But the nice thing is we actually have an average up front here. So we can now do this update based on samples, based on sample-based averaging. The max still appears. We didn't fully get rid of the max, actually. It appears over here. But this is not a problematic place for the max to be. This we can do. We're now keeping track of Q values, a value for each state, each state action pair. Well, in that table, we can look up for state S prime over all actions A prime, which one achieves the highest value. And we can fill that in here and compute our sample-based estimate, which is this entire thing over here in this Q value iteration process. All right, so let's take a look at how this works. This is our update equation if we do it exactly. If we do it sample-based, whenever we get an experience, which means SAS prime and the corresponding reward, we receive a sample SAS prime and a reward R. We consider our old estimate, QSA, our new estimate based on the sample. Of course, the sample isn't necessarily better because there's a lot of stochasticity. It's just a sample. We don't want to just replace Q of SA by the sample. We want to nudge it towards the sample a little bit. And so our update is as follows. we average what we had with the sample, and again, this exponentially moving average, such that the old things, which aren't all that accurate, get lower and lower weight over time. The new things have the higher weight. Same thing as before, for this to be guaranteed to converge, your alpha has to go to 0 over time. The alphas that you use have to sum to infinity, but their squares have to be summing to something finite. Okay, algorithm-wise, this is fairly straightforward, right? This is all you do. It's a very simple thing to implement. That's part of the beauty of Q-learning, is that this is all you need to do. You just have a table with Q values. You see a state action state triple and the reward associated with it. You update one entry in your table of Q values, and that's it, and you keep going. Let's look at a demo to see how this plays out. So what we have here is our grid world, standard grid world. Initially, well, we're running reinforcement learning. We initialize everything to 0. We don't know what to do. I'll be choosing the actions right now. So I'll choose northeast, southwest. A full algorithm would also tell us what action to choose, and we'll get to that on the next slide. But for now, I'll choose the actions. And we just want to see what happens if we run Q-learning. So first thing I'm going to do, I'm just going to go up and off to the right. Everything is still 0. We actually did Q-learning updates for each of these state action pairs that we visited, but nothing happened because it all stayed 0. Now is the first time that we'll see something change. Once we take the exit action here, the sample estimate of the Q value of the exit action here will be different from 0. The weighting factor here, I think, is 1/2. Yes, so we have alpha equal 1/2. The reward was 1, so our new sample estimate is 1. It was 0 before. We weighed 1/2, we end up with 1/2. We go again, north, north, east, east. At this point, we know after taking the action east, assuming it's successful and lands in that the state from which we can exit, we know the sample value will be different from 0 because the reward will be 0, but the best Q value in the state you land in, the max overall Q values in that state is 0.5. And so we'll see an update here and it'll become 0.25. There we are. How about this one here? We take the exit action. The reward will be 1. That will be the sample estimate because after the 1, the value is 0 at all times. So the sample estimate is 1. That gets averaged with what we have right now, which is 0.5, and we end up with 0.75. Go up, up, east, east. We saw an update here. We got 0.12. And as we keep acting here, you see these values propagate out and taking on more and more meaningful values. Which are the ones that are getting non-zero values? Only for the state action pairs that we actually visited do things change. Right? For a lot of these states, we've never taken the 3 other actions, or even all 4 actions, and the values just remain 0. So the reason we have a 0.11 there for the up action is because one time I went up, and it had an update there. When you go up, what happens? The reward is 0. You stay in place. But the sample is not just the instantaneous reward. It's also the value of the state you land in. The value of the state you landed in is the same state in this case. It at the time had some certain value. That was added to it, then averaged with the current 0, and you end up with the 0.11 at the time. So let's take a look at this more closely over here. Let's say over here, I would take the action down. What's going to happen? Take the action down, everything stays 0. Because the sample estimate, which is the reward plus value at the next state, is 0. What if we go up from here? Value will go up, right? What if we go off to the right from here? So let's go to the right. Initially, nothing happens. That one updates. Now let's go there again. Now it's going down. And let's keep doing this. So let's keep going here and see what Q-learning does for us. So what's interesting here is that the value for this action here to go down is still 0. Why is that the case? Going down has a reward of 0. The best value you can get from that next state down here is still 0. That's the estimate for the best value. And so this minus 0.81 doesn't affect the value of that state up from it. All right, so this is one interesting property of Q-learning, is that even though, if you look carefully at the values, I started acting rather suboptimally here, and going through a lot of these states, taking the same actions I've taken before, these values are still going up. You see these values were still going up even while acting suboptimally, because it knows that the optimal value from the next state is actually a high value. And it's using that. It's not using the outcome from this particular run. It's using the value of the next state in its sample estimate, not what happened to be happening in this run. So it can be acting suboptimally and still be learning good things. Let's do this again. So again, here we have the process of these Q values propagating, and they're still pretty low on the left here. But even if I now start acting suboptimally, these values will still propagate in the right way, in the way that we want them to propagate, based on the actual best value estimates, not what happened to be the outcome. And we see that we will get this value of 1 essentially propagated all the way back if we keep going long enough, despite the fact that we are currently never actually incurring that positive reward. I guess here we did, because I pressed the buttons too quickly. But in principle, we never need to go there again to get that thing to propagate back. Why? Because whenever we are over here, or consider the value of this state, it's based on what happens from there, what the best thing is you can get there, not based on what you're actually doing, which is going down. This is called the off-policy method. You're learning something about actions that are not the actions you are necessarily taking in your exploration phase here. Because what I'm doing is in some sense exploring. I'm exploring how the system works. It's updating its Q values, and it's learning some Q values that are not even the ones for my bad policy, but better Q values. All right, so that's a first demo. Then let's take a look at the crawler. In which square? We were only showing Q values and not rewards, yes. The exit states are the only ones who have rewards in that example. Here's our crawler again. This is a two-dimensional state space because there are two joint angles for the robot that determine the state. So horizontal axis is one joint angle, vertical axis is another joint angle. They're discretized here, so we have a discrete set of states. On the left, what you see is the value estimates of the states. This is running Q-learning. On the right, you see the Q function estimates, so 4 per little square. And so you see as it is exploring, and the way it's exploring here is by 80% of the time taking a random action, so it doesn't just look at its Q function value and take the optimal one according to its current estimate, because it knows that initially those Q values aren't all that good. So just following those is probably not the right thing to do. You need to try things out, see what happens. We also know from what we've seen, we haven't seen a theorem to this extent, but the example we saw in the grid world was that if we act randomly and we see enough actions and states and so forth, somehow this Q-learning finds the right Q values. Right? After a while, we'll drive down the exploration amount here, and it'll start acting more greedily. Right? It'll more often take what it thinks with respect to the current Q values is the right thing to do. Is it good? Well, it doesn't have that much experience yet. It's making progress. It's not exploring it all that much anymore. If you want to explore more, you drive this back up, the probability of taking a random action, and it might start exploring different parts of the space. Looking at this, one thing, of course, that you notice is this random exploration doesn't necessarily get you to explore very effectively, right? You're just randomly moving, and, well, if you have a long hallway and you randomly move, it can take a real long time before you decide to make that every time move in the same direction until you finally get to the end of the hallway, right? But it learns. It's learning, and we know that if we skip far enough ahead, in this case, a million steps, we get these beautiful Q values. And if we now drive down the probability of random actions, we just start acting what it thinks is optimal according to its learned Q values. This is what you get. It's nicely moving forward, which is off to the right. It's not in a fixed state. So if we're walking here, it's not the case that a particular state is the one you can hang out in and get high reward. You have to go through a cycle of states. Some of these states are actually pretty red colored, not very green. That's just part of how the system works. In that those states are just not as good, but you can't just always stay in the green states. That's just the way the transition model works out. All right. So Q-learning has some great properties. We haven't proven this, but Q-learning converges to the optimal policy even if you're acting suboptimally. This is called off-policy learning. We learn about the optimal policy even while acting according to a different policy. There are some caveats, some fine print here. It's important what actions you take. It's somewhat arbitrary, but not totally arbitrary. You have to explore enough. So that means randomness is good, but if you have a fixed policy, well, if you fix your policy, you're not going to be able to learn about actions that never occur in that fixed policy, right? So you need to see every state action pair infinitely often. If you do that, then this will converge to the optimal Q values. Hopefully soon enough, it'll get close enough. But that's the thing. Exploring enough means every state action pair needs to be seen sufficiently often. The learning rate, which is our alpha, needs to decay over time, but not too quickly. We've talked about that. In the limit, it doesn't really matter how you select your actions as long as you see every state action pair infinitely often. All right, so this brings us to explorations versus exploitation. We want to start explicitly thinking about how do we explore more effectively than taking just random actions, right? Why do we care about exploration? We had the blue versus the red bandit last time. Here, let's say a new restaurant opens in Berkeley. It's lunchtime. You could go to your usual place where you know you're getting the food you like, or you could go to the grand opening, the first one to ever get food in this new place. Well, what are you going to do? Not sure, right? You kind of have to try the new place, see how it plays out, and then based on that, you might maybe try it again because maybe you ordered the wrong dish. And after a while, maybe you give up, or maybe after a while you realize this new place is your new usual place, and that's where you keep going. So exploration is really important. While you explore, you might be suboptimal, but it's part of the game here. You don't have a transition model. You don't have a reward function. You need to find out through acting what the right thing is to do. Okay, a very simple scheme called epsilon greedy is where at every time step you flip a coin with some small probability epsilon, you act randomly. So the coin flip with probability epsilon comes out one way, probability 1 minus epsilon comes out the other way. Comes out the first way you act randomly, comes out the second way you act on the current policy. What do I mean with current policy? Well, you've been learning this Q function, right? So you can look up in that table, according to your current estimate of the Q values, what's the best action to take? What's the problem? Well, it can take a long time to get anywhere. You're not exploring in a very directed way. You're not going to places you don't know much about in any dedicated way. You're just every now and then doing something random. Another option is that, well, if you're always continuing to be random with some probability epsilon, then at the end, you're still not acting optimally because you're often throwing in a random action. So you need some way of getting less random as you know that you learn the better estimate of your Q values. So in practice, you would lower your epsilon, as I've done in these crawler demos, after you've learned enough. So probably gradually lower it over time, but not too quickly. There's still this issue here is that you're kind of just bouncing around, checking things out, but not really going places to explore them. How can we change that? There's something called exploration functions. It's a really neat idea. And the idea here is that you explicitly encode value of exploration in your Q function. Here is the regular Q function update. Here's the new Q function update. What's different about it? There's this new thing here at the end, some function f that considers your Q value and this quantity ns prime a prime. That quantity is counting how often have you been in state S prime and have you taken action A prime. The intuition here is that if you have not often been in state S prime and taken action A prime, you should favor that. And so you want to favor that, and that's coming in here because what you do is you take this function f here, the first argument gets retained, but then adds what is called an exploration bonus. You add value if you do something that's explorative. So the lower this n s prime a prime is, which happens to appear at the bottom here, the higher the exploration bonus. And once you've seen a state action pair, very often the exploration bonus for that state action pair goes to 0. This has two effects. One effect is in your action selection, right? When you do your action selection now, based on this Q function, well, exploration will explicitly pop up, right? It will come in, right? After this update here, an action, well, the biggest effect is that it changes here, but kind of the propagated effect is really what helps you, is that what's happening here now is that for an action A, where at the next time you would land in a state S prime, where a lot of exploration is available, and that action A in the current state S will get a higher Q value. So the Q value for SA goes up thanks to S prime having exploration available. And this will propagate throughout your state space. So you will see Q values propagate just like we saw them based on reward before. This bonus reward, exploration bonus reward, will propagate throughout your state space, throughout your Q value table. And you will start taking actions that lead you to states that in turn can lead you to states that can lead you to states that lead you to states and so forth to finally lead to a state where you have an exploration action available. You will get that behavior. So let's take a look again at the crawler and see what happens if we, rather than this epsilon greedy kind of exploration, we use this exploration function. Remember, to learn in the past, we've had to do this, let's skip 1,000,000 steps and see what happens after 1,000,000 steps. Here we're using an exploration function, and we're just watching all the trials. It's exploring in a more dedicated way. If it has seen things many times before, the exploration bonus goes down, and you won't see it repeating it that frequently again. So the kind of part of the space where it's not touching anything, it's starting to learn that there's not much exploration left there. Now it's exploring this other part of the state space. It's getting a lot of actual reward there. And in just a couple of seconds, it has learned to make progress on this problem, pretty much as well as we before had after 1,000,000 trials, just through a much more focused exploration. Yes? The other one after 1,000,000 trials, it might depend a little bit more on luck because it doesn't explore as dedicatedly. Sometimes it might be pretty high up, sometimes low. Another thing that could play a role is if you're doing random exploration, you have to switch off that epsilon back down to 0 to compute your average speed to see what you have learned, right? So if you run the old one over here, right, and we skip ahead that 1,000,000 steps, right? After skipping ahead 1,000,000 steps, we should now lower this over here so we are actually acting according to the Q function we learned rather than according to, with probability epsilon random, which now epsilon is 0, so that's okay. And so we were now up to 0.3, which is a higher value than what we had, I think what you remembered from previous time. But the beauty with the exploration function is that you don't even have to manage this. It automatically decays the bonus for exploring new things as you've seen things frequently. They're not new anymore. The bonus is lower. Okay, where are we at so far? We've seen what to do if we know the MDP. We can find an offline find an optimal policy through value iteration or policy iteration. So let's actually overwrite this and make this iteration. If we don't know the MDP, we've seen many methods today how to deal with it. So what's left? What haven't we done yet? We haven't looked yet at whether the state space is so large that you can't feasibly iterate over all states when you were to be running value iteration, or you can't expect to visit every state when you're running Q-learning. That's what we'll look at next lecture. And for example, we'll be able to tackle reinforcement learning in Pac-Man then, which is a very large state space.